Coordinate Systems and Map Projections Introduction. 1. Purpose of Coordinate Systems and Projections. The chapter introduces the necessity of coordinate systems and map projections in GIS, which are essential for accurately representing the Earth's curved surface on flat maps and for ensuring that spatial data can be correctly interpreted and analyzed. The shape of the Earth. 1. Geoid. The Earth's shape is not a perfect sphere but an irregular shape called a geoid, which represents the mean sea level across the globe. 2. Ellipsoid. For mapping and GIS purposes, the Earth is often approximated as an ellipsoid, a smooth, mathematically defined shape that is slightly flattened at the poles and bulging at the equator. Geographic Coordinate System. 1. Latitude and longitude. Latitude measures the angle north or south of the equator, 0 degrees latitude. Values range from 0 degrees at the equator to 90 degrees at the poles. Longitude measures the angle east or west of the prime meridian, 0 degrees longitude, which passes through Greenwich, England. Values range from 0 degrees to 180 degrees east or west. 2. Datum. Definition. A datum is a reference point or surface against which measurements are made. In GIS, it refers to a model of the Earth that defines the size and shape of the ellipsoid and the position of the ellipsoid relative to the Earth's center. Types of datums. Local datums, based on a specific region and align the ellipsoid with the geoid in that area, e.g., NAD27 for North America. Global datums, align the ellipsoid globally, making them suitable for international mapping, e.g., WGS84. Map projections. Purpose of map projections. The process of transforming the curved surface of the Earth onto a flat map. Since this transformation involves distortion, different map projections are used depending on the purpose of the map. Types of map projections. 1. Conformal projections. Preserve local shapes and angles but distort area and distance, e.g., Mercator projection. 2. Equal-area projections. Preserve the area but distort shape and angles, e.g., Albers Equal-Area projection. 3. Equidistant projections. Preserve distance from one or 2 points to any other points on the map but distort area and shape, e.g., azimuthal equidistant projection. 4. Compromise projections. Attempt to minimize distortion in all aspects but do not preserve any single property perfectly, e.g., Robinson projection. Projection parameters. 1. Standard parallels. The latitudes where the projection surface intersects the globe, minimizing distortion along these lines. 2. Central meridian. The line of longitude that is the center of the map projection. 3. Projection center. The point where the projection is centered, typically the Earth's center or a point on the surface. Commonly used map projections. 1. Mercator projection. Used for navigation because it preserves angles, making it useful for maritime charts. 2. Transverse Mercator projection. Commonly used for large-scale mapping, particularly in the Universal Transverse Mercator (UTM) system. 3. Lambert Conformal Conic projection. Often used for aeronautical charts because it preserves shape in mid-latitude regions. 4. Albers Equal-Area projection. Used for maps where area accuracy is critical, such as in statistical mapping. Coordinate systems in GIS. Geographic Coordinate System (GCS). 1. Based on a 3D spherical surface. Uses degrees of latitude and longitude to define locations on the Earth's surface. 2. Commonly used datums. WGS84, 83 Namibian dollars, NAD27. Projected Coordinate System, PCS. 1. Flat, 2D representation. Converts latitude and longitude into linear units like meters or feet. 2. UTM system. Divides the world into a series of zones, each with its own transverse Mercator projection, minimizing distortion within each zone. 3. State Plane Coordinate System, SPCS. A set of coordinate systems used in the United States, dividing the country into zones with minimal distortion within each zone. Coordinate transformations. 1. Purpose. Converting spatial data from one coordinate system to another is often necessary in GIS to ensure that different datasets align correctly. 2. Transformation methods. Georeferencing. Aligning spatial data to a known coordinate system by matching points in the data with known locations. Affine transformations. Linear transformations that preserve parallelism and straight lines, typically used for scaling, rotating, and translating data. Accuracy and precision in coordinate systems. 1. Accuracy refers to how close the measured coordinates are to the true values. 1. This is affected by the quality of the datum and the precision of the measurement tools. 2. Precision. The level of detail in the measurements, often represented by the number of decimal places in the coordinates. Summary. 1. Key takeaways. Understanding coordinate systems and map projections is critical for correctly interpreting spatial data in GIS. 1. The choice of coordinate system and projection depends on the geographic area of interest and the specific requirements of the analysis. Important concepts to remember. 1. Geoid versus ellipsoid. Know the difference and why ellipsoids are used in GIS. 2. Datum. Understand the concept of local and global datums, especially WGS84. 3. Map projection. Be familiar with different types of projections and their specific applications. 4. Coordinate systems. Differentiate between geographic and projected coordinate systems, and know when to use each. 5. UTM and SPCS. These are commonly used projected coordinate systems, especially in regional and local mapping projects. Study tips. 1. Visualize projections. Use online tools or GIS software to visualize different map projections and see how they distort the Earth's surface. 2. Practice with coordinate systems. Use GIS software to work with different coordinate systems and understand how transformations affect spatial data. 3. Understand transformation methods. Familiarize yourself with georeferencing and affine transformations through practical exercises.